You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dan Werthimer. Dan Werthimer is the co-founder and chief scientist of the SETI Home Project at the University of California, Berkeley. He specializes in signal processing for radio astronomy. He has been doing SETI since 1979, and he runs the SERENDIP, Optical SETI, and CASPER projects. Remember to subscribe to Event Horizon so you never miss an episode.
Dan Werthimer, welcome to the program.
Nice to be with you, John.
Now, Dan, you've been involved in something that is very, very close to my heart as a science fiction author for over 35 years now, SETI, and looking for any signal we can think of that might indicate the presence of an alien civilization somewhere in the Milky Way. Now, when you started this, were you bullish? I mean, did you think that we could easily find a signal? And how's that versus today? Do you think that with increasing technology, we may well nail this within a few years, or maybe it's a little bit further away?
Yeah, it might be 100 or 1,000 years. SETI is a multi-generational thing, and people have been thinking about how we might detect ETs for maybe 1,000 years, but there were early ideas for how to do this 200 years ago with fire and geometric structures and using mirrors to reflect light to the Martians. And those ideas we laugh at them today, but I think that means 200 years from now, people will be laughing at what I'm doing and say, why didn't Dan use tachyons in subspace communication? So I don't know if we have the right technology and science to do it now, but we're getting in the game. Earthlings are an emerging civilization. We're learning how we might be able to communicate with other civilizations.
I think that's an interesting point, that the very earliest attempts at METI were 200 years ago. Somebody just suggested, all right, let's arrange some agricultural fields and maybe get someone's attention if they're looking at us with a telescope. And
Gauss.
Yeah, Gauss.
Gauss was the mathematician that suggested that. And he said, let's make a thing that lets ET know about the Pythagorean theorem, that we know about the Pythagorean theorem with big squares and triangles of wheat, wort, and dirt. And that ET would see this huge geometric structures, maybe a right triangle, 3, 4, 5 miles on a side or something, and they might get in touch with us.
Clearly, we probably didn't do that, but that does telescope to today. I read a paper relatively recently about maybe you could detect alien agriculture at a distance, a biosignature of that's altered in some way because of alien agriculture and the introduction of nitrogen as a fertilizer and things like that. So maybe he wasn't that off base.
No, I think those early ideas at the time were pretty spectacular ideas. This idea that we could detect the presence of simple biology biosignatures instead of technosignatures. SETI, as you know, is a search for technological artifacts so they have to be an advanced civilization. But the biosignatures, we could detect maybe primitive life, plants, trees, maybe bacteria. That's something that we can't do. Earthlings can't really do that right now, but it's coming very soon. And JWST is getting us a little closer, but I think it'll probably be the next generation after that before we have the technology where we could take the spectrum of an atmosphere, divide the light up into colors. That would tell us which molecules are in the atmosphere. Oxygen, if we find oxygen, that would indicate maybe photosynthesis, plants. And there are other, as you said in your question, there are other molecules that would indicate maybe bacteria. And people would argue about whether this stuff could happen sort of by nature alone or whether it's an indicator of life. But if you found a combination of chemicals, that would make us more certain. But there was no oxygen on our planet until life came along. When the Earth got started, there was no oxygen. Life makes the oxygen.
And also kills the original life, the great oxygenation event. So the original...
Right, oxygen is poisonous to most life, yeah.
Yeah, so the anaerobes had to retreat, but they're still here. They just can't live out in the oxygen atmosphere. Now, biosignatures versus technosignatures. So with SETI, you're searching for extraterrestrial intelligence, and you're looking for very technological things like radio signals that are narrowband and output at certain frequencies and maybe have modulation and things like that, versus planets that just have microbial life that's altering the atmosphere. Which do you think is more likely for us to detect? So as we build better telescopes, we can look for biosignatures and look for weird atmospheric gases and things like that that are in disequilibrium and shouldn't be. Or versus a big, huge radio beacon that everybody in the galaxy can see. What are the likelihoods, you think, for either one? Which one do you think we will find first?
That's a really hard question. Right now, almost all the money is going into the biosignature stuff. Very little is going into SETI or technosignatures. But I think there may be like a 50-50 chance. I don't know where I'd bet. The technosignatures, you point out, we could detect from a distant galaxy if there's an advanced civilization. We could look at 100 billion stars at a time. The biosignatures, we have to look nearby, and we don't even have the capabilities yet, but we will have those capabilities, and we could look maybe at nearby stars' atmospheres, but not a lot of stars, at least in the next 50 years. We won't know how to look at a lot of stars. We can only look at the nearby stars' atmospheres. There's another kind of biosignature thing that I'm excited about, which is looking in our own backyard, in our own solar system. You probably know there are a couple of moons that might have life on them. Enceladus is a moon going around Saturn. Europa is a moon going around Jupiter. And both of these moons have liquid water, oceans. And they probably have these thermal vents at the bottom, which means there's a big source of energy and probably a lot of organic molecules. We think that's where life got started on Earth, at the bottom of the ocean, where these deep thermal vents are. And so there may be something swimming in these oceans. And there is a problem. The oceans are covered with ice, about 30 miles thick crust of ice. But we're trying to figure out how to get down there. And Enceladus, you don't even have to get down there because there are cracks or fissures in the ice, and some of the liquid water in the ocean is getting up through the cracks and forming a kind of plume that we might be able to fly through and sample and see if there's some life or little pieces of life in the water that's kind of going up like a geyser.
Now, would you say it's fair to ask the question, first find the microbes in such a situation? So you're flying through this plume at Enceladus and you're trying to sample it. You're pretty much looking for microbial life rather than, a frozen space fish or something like that.
And you'd probably be flying through faster than a bullet. And so you're not going to find life, but you might find little pieces of life when you hit it. Little fragments of RNA or DNA or some long molecule or something that would indicate life.
Is that how you design the experiment, to look for some section of what might be RNA or DNA or something like that? Is that how you design such an experiment?
Well, there are lots of ideas for doing that. If it was alive, you could kind of feed it and see if it ate something and see if it outgassed. But if you crush it because you're flying so fast through the plume, if you use a lot of energy, if you had a really expensive mission, you could slow down and get into the orbit. But if you fly right through it, that in kind of the minimal energy way, you're just going to smash it all up into bits. And then you just got to look at the little bits. It's very much like the particle physicists do when they're trying to figure out what's in the nucleus of an atom, what's inside those particles. They smash the atoms together and all these bits fly out. It's like smashing a watch and then try to figure out how a watch works by all the parts that fly out when you hit it with a hammer.
So that's still easier to do than a direct detection, like landing and drilling down into the water.
No, I think that would be more conclusive. If you go at it, then you wouldn't have to destroy the life by smashing it up into bits. So, but that's harder to do, of course. I was talking to a middle school class and a 13-year-old girl. I usually give the kids a question like, how are we going to get through the ice? And the boys, they usually want to use bombs or machine guns or some way to get through the ice that's kind of a violent technique, dynamite or something. The girls have more passive techniques. They suggest let's melt our way through, maybe use mirrors to, reflect the sunlight or magnifying glasses or something to heat our way through. And there was a young girl who said, could you build a small radioactive submarine, maybe a half a meter long, and coat the hull of the submarine with a radioactive material that has a short half-life, so it would get hot, it would stay hot and melt its way through the ice. And could you coat the hull of the submarine, the radioactive hull that's getting hot, coat that with thermopiles to generate electricity for the submarine? So I think there is hope for the world. These young women have some very clever ideas.
Interesting. Now, if you had to place likelihoods on life at an ice shell moon like Europa or Enceladus, do you think that we are looking at microbial as a rule because of the conditions present, or do you think we could actually have some kind of complex life, macrofauna maybe, space whales? Do you think that the bet that that we live in a microbial universe predominantly is a better one as opposed to one where they have things like us?
Well, most of the life on Earth is microbial. They're more successful creatures than we are. They've been around billions of years. There are lots more of them by any measure. We've only been around a few 100,000 years on this planet, and who knows how long we're going to last. We might last another billion years. Our sun's going to be around for another few billion years. Most planets are older than we are. We're kind of middle-aged. We're 5 billion years old. But some planets are 10 billion years old, so there could be very advanced life on them. I think that primitive life is much more likely in our own neighborhood. They're not going to be, I don't expect to have, multicellular creatures or advanced life. Because of those conditions, there's not strong selection pressure for advanced life. I think primitive life could succeed quite well in the oceans. On Earth, because we have this complex environment on land and sea and the interfaces between the atmosphere and the land and the sea, there are selection pressures which make it, there are lots of ways to succeed in evolution. You can run fast or have a hard shell, but you can also be smart, and that can be advantageous in some. So there could be selection pressures to be smart on Enceladus and Europa, but probably I would guess it's going to be very primitive life. But it's still fascinating. If we discover life in our own backyard, that means the universe is filled with life. If it happened twice in our own solar system, that's pretty spectacular. The universe is teeming. But there is a little caveat there. If the life that we discover on Enceladus, Europa, or Titan is exactly the same as life on Earth, it has exactly the same amino acids, exactly the same chemistry, built exactly the same way, RNA, DNA, that's not very interesting. That probably means there was only one place where life got started. And we know there are rocks flying back and forth around the solar system. We have some rocks from Mars in our lab that a big rock smashes into Mars. All this stuff goes flying everywhere, pebbles, all kinds of stuff. And eventually some of it happens to hit Earth. If you go to Antarctica, if you find a black rock on the snow, you can kind of analyze what it's made of and what the trapped gases are and figure out what planet it came from. So there could be this idea that maybe life got started on Earth and rocks traveled from Earth to Europa and seeded life on Europa. That's not as interesting as if it's a different chemistry. If we find out it's made of some different amino acids, there are a couple hundred amino acids, and we just happen to be made out of 20 that were probably around right at that particular time. We could have easily been a different 20 out of 200. So if it's different chemistry, that means that life formed independently in our own backyard, and that means that the universe is teeming with life.
There is a consolation prize, though. If you find life, microbial life, that is related to you elsewhere in the solar system, you get to ask the question, where did life originate? Did it?
Yeah, we could be the Martians or the Europeans or the Enceladians. In my example, I said life might get started here, but it could just as easily be that it started there, and we're not Earthlings, we're Europeans.
Or Martians, and we're about to retake the home world if certain billionaires realize their dreams. Now, there's another way, though. With microbial life, it's a twofer because you could find it at a place like Enceladus or Europa, but it could also pop out of a test tube in a lab. So these origins of life experiments that people are doing and making some progress with could also answer the question and equally tell us the universe must team with life if the process is easy. And so we have two ways within our lifetime to see that. Aliens, as far as intelligent civilizations, maybe not, but we have at least two ways to do it here on Earth with what we're doing right now.
Yeah, these things where you try to create life in a test tube, there were some early experiments in the 50s by Urey and Miller. What they do is they put in some ammonia and some water and carbon dioxide and things that they knew were around when the Earth was forming. And they put in some sparks. You get, like, because we knew there was lightning 4.5 billion years ago. And they didn't get gorillas crawling out of their test tube, but they did get kind of the basic building blocks, the amino acids and the things that you and I are made of, pretty complicated molecules. So they're beginning to understand how life got started. We don't really understand the details of that process, but we do know that life got started on Earth very early. The oldest rocks you can find, just as soon as the Earth cooled down, have microfossils on them. And so because it didn't take long for simple life to get started on Earth, we think it's probably pretty common in the universe.
The elephant in the room with SETI is that we look out and try to detect alien civilizations and have done so for a very long time. Project Ozma and very early attempts to SETI all the way till now. And the thing is, we have candidates that we can't prove, most famous being the WOW signal. I interviewed Dr. Jerry Eman, who circled the data on the printout, and we still don't know what that is. As a SETI researcher, are there signals that you've seen that haunt you, that maybe that was it? Maybe that was an interception of a technological signal that we simply never saw again?
Yeah, the first part of your statement is we've been searching for a long time. But I think Earthlings are an emerging civilization. We're just getting in the game. My guess is we don't quite know what we're doing yet. We have all these different ideas of what to do. And it'd be very surprising right now with our very limited searching that Earthlings have done. There's such a big problem in SETI. We don't know where to point the telescope. We don't know what frequency they might be broadcasting, what signal type. There's a huge amount of unknowns. And there's so much, we call it search space, to cover. We're just scratching the surface, just getting in the game. We barely put a little down payment on searching. So it would be surprising that Earthlings could run into a signal either accidentally leaving their planet or a deliberate signal right now. So that part, I'm not bothered that we haven't found ET yet. I think it might be a while. The good news is that we're growing by leaps and bounds, the exponential growth in computer technology and telescope technology. A lot of it's limited by computing. The more computing power you have, the better job. Anyway, the other part of your question was about these candidate signals. So everything so far that we found has always turned out to be radio pollution. We call it radio frequency interference or radio interference. And it comes from satellites, airplanes, cell phones, radio stations, television stations. And the Earth is getting more and more polluted with radio signals. And it's getting harder and harder to do SETI from the Earth, anywhere on Earth. We usually put the telescopes far away from people, but they still encroach. And the satellites, now there are more and more. There's thousands of satellites now, and you can't stop them from broadcasting. And they're above the antenna no matter where. And Earthlings we may end up having to go to the backside of the moon and build a big telescope there. Then the moon would act like a big shield from all the radio pollution from Earth. And some radio bands, like television bands, FM bands, Wi-Fi bands, we just can't search for ET there anymore because they're just so polluted. The signals are very strong in those bands. If ET's broadcasting it in one of those bands, then we'll never be able to find him unless we get away from Earth and maybe go to the backside of the moon. So this may be a kind of unique window in Earthlings history where we have the technology and where we might be able to detect ET, but not all the parts of the electromagnetic spectrum are full of our pollution. The WOW signal, I think is kind of the least likely place where ET exists. It's been checked by hundreds of people with much more powerful and much more sensitive searches, because the technology has gotten so much better since that WOW signal was found. It was almost certainly interference, probably a satellite going over there. And it was not. The plan was that they had two receivers, and that if it was a distant civilization, it would first peak up in the first receiver, and then a little while later, it would pick up in the next radio receiver as the Earth rotated. And they never saw it pick up in the next the receiver. So it's pretty obviously our interference. If it were ET, it would have been seen in both receivers. But there are candidates. We have about 100 candidates from SETI at Home, but nothing we're hopping up and down about.
So at SETI at Home, which I was a participant of for a number of years, it was my favorite screensaver. Is that going to make a comeback? I mean, can that same technique still be useful in SETI today in a new form?
Yeah, I think it would be, and we're looking into that. So SETI at Home ran, you probably know, for 20 years on what was the world's largest telescope, the Arecibo telescope in Puerto Rico. And we were running almost 24 hours a day because we could use that telescope while other astronomers were doing their research, mapping the galaxy, studying pulsars or fast radio bursts, or whatever they were doing. We would just go along for a ride. And astronomers tend to point in interesting places, and some of them do big sky surveys. So it was like almost as good as getting the telescope to ourselves, just, year round for 20 years. Most astronomers are lucky to get that telescope a day or two a year. It's very competitive. So we did this big search, and we were able to form one of the biggest supercomputers on the world. We had 8 million volunteers in 200 countries with their home computers, everybody analyzing a different part of the sky with their SETI at Home screensaver. When the Arecibo telescope collapsed, we put the project in hibernation. It's not the end of the project. We're still analyzing the data that all the participants donated. We're very grateful to all the computing power that they donated. And that we're going through it, looking at our best candidates. We're going to go to a big telescope in China, the world's biggest radio telescope in China, called the FAST telescope, 500 meters across, holds about 20 billion bowls of cornflakes. And we're going to use that telescope to look at SETI Home's best candidates. We're also exploring using another telescope to collect data and send it out to the SETI at Home participants. But we're not there yet. We're just in exploratory talks with different observatories.
Any hope of building a radio telescope dedicated specifically to SETI? Now, of course, we have the Allen Telescope Array, and these such things exist. But is there anything that could be done? I mean, rebuild the Big Ear or something like that. Maybe a radio telescope on the cheap to try to get data that SETI at Home can chew on.
Well, SETI at Home really is better off to use a really big telescope when you do SETI, and that would be an incredibly expensive thing. And these telescopes are $1 billion, a big one. And that is out of the range for SETI budgets. You can use dedicated telescopes and build your own, like the Allen Telescope Array, but those are relatively small telescopes. You need to have a very strong signal to receive something at the Allen Telescope Array. So there's pros and cons of doing this. If you have a dedicated telescope, you could point it exactly where you want. You might try nearby stars, or you might try distant galaxies, or probably maybe interesting things in the sky. I think it's good to do both kinds of things. Use dedicated telescope, dedicated time, but also I'm very excited about this idea of what we call Commensal SETI, where you use these huge telescopes, the world's best telescopes, the most expensive, with the best receivers and the best equipment and the huge collecting area. So you can be very sensitive, and you do them at the same time that other astronomers are using the telescope. We call it piggyback SETI or commensal SETI. We just call it parasitic SETI, but it's not really damaging what the other astronomers are doing. We can do it on a non-interfering basis. And that way you get these telescopes, they cost $100 million a year to operate, some of the biggest ones. So it would be very expensive for us to build something like that. So I like the idea of just kind of using other international facilities, and that way you get to use the best telescopes. But I also like the idea of using dedicated telescopes. You can't afford to make a really big one, but that could be a small telescope. You can do interesting things like stare at something for a really long time. And I can talk about that a little bit later. And so, anyway, there are lots of things you can do if you point your telescope at a really interesting place and you have a lot of time to do. I think the best strategy in SETI is a multiple strategy. We really don't know what TET might be doing. And so I like the idea of doing something, a lot of different things: optical searches, infrared searches, radio searches, artifact searches, Dyson sphere searches. Try a lot of different things. We like to launch a new thing every year.
Now, with the FAST telescope, China has a magnificent telescope. From what I can say, this is an amazing thing that they've done. And they've made it clear that they intend to engage in SETI with it in addition to radio astronomy. And my question to you is, as a researcher working within the field of SETI, what are your hopes there? I mean, does it look like they're just going to have an open, altruistic scientific telescope for everybody to look at? Or do you think that the situation of international politics will confound it?
So the FAST telescope is probably the best place to do SETI right now. And we've been working with China. I've been going there every year, not the COVID years, but working with them to help them build a telescope and get the SETI instruments on the telescope. And they have really great facilities and great astronomers. And we've been doing lots of different SETI experiments on that telescope. It really is a brand new telescope. But it's already made some incredible astronomical discoveries, and it's working really well. And so we're doing two different kinds of SETI search. One is we get dedicated time. And by the way, anybody can use that telescope. It's open to any astronomer. You write a proposal, and it's free to use it. If you write a good proposal, they will give you time on that telescope if it's interesting. And we've been able to get time with our Chinese colleagues to do targeted searches where we have dedicated time and we can point to nearby stars and do kind of detailed searches at lots of different frequencies and look for a long time at those stars. And we also doing this big 5-year sky survey on the FAST telescope. And we're using a huge amount of telescope time on the world's largest telescope to do this sky survey. But it's not just for SETI. There are 5 things going on simultaneously: mapping the galaxy, mapping maps of other galaxies, searching for pulsars, searching for fast radio bursts, and doing SETI. We're all scanning the sky simultaneously.
Any chances for rebuilding Arecibo in some form in the West?
Well, there's a lot of discussion about that. There's some interesting designs of how to rebuild the facility, and NSF, and NASA have been looking at these ideas and figuring out how much it might cost. And it's going to be a pricey thing. There's not much money for astronomy at the National Science Foundation these days. The budgets are pretty tight. And it's going to be hard I think, to raise the money. I hope they do, because it's not only a spectacular scientific field, but and a great opportunity to do science there. But Puerto Rico could really use Arecibo or something like Arecibo. They've been really suffering with hurricanes, and there's still people that don't have electricity there. There's a lot of financial hardship in Puerto Rico. And this was their big flagship. Every kid in Puerto Rico took field trips almost every year to the observatory. They were so proud of it. And it was a vehicle for teaching kids astronomy and getting them working at Arecibo and finding, really interesting science and engineering jobs at Puerto Rico. So it would be a great thing to be able to rebuild it at that island, not just for science, but for the Puerto Ricans as well.
Oh, I'd agree. If we're going to rebuild it, let's do it right at that same site within Puerto Rico and keep everything going. But also, there's a reason that telescope was there, because you're getting close to the equator. So there's a scientific reason to rebuild the telescope there, right?
At the time, that facility was very quiet. There wasn't that much radio pollution. Unfortunately, it's getting noisier there. The great thing about why the telescope was built in Puerto Rico near the town of Arecibo up in the mountains is they have this geological feature called karst. And karst is these limestone things that sink in when the water flows under the limestone. and you get these valleys that are shaped like a telescope, like a giant parabolic dish. So, this is a valley that is a couple kilometers across, a mile across, something like that. And it's got a good shape. And you can put a dish in this pit. And China did the same thing, by the way. The FAST telescope is in this karst region in southern China where you had these valleys. So you don't have to do a lot of bulldozing, which would be incredibly expensive to move the ground. The ground was already in the right shape.
That's interesting. So you say karst topography in China. So basically it's built in a sinkhole, essentially?
Yeah, it's exactly right. A sinkhole.
Huh, interesting. I didn't know that. But it does make sense. Make Earth move your soil rather than doing it yourself. With FAST and SETI searches there, how closely does this mimic the abilities of Arecibo before we lost it? I mean, can, for example, we actually transmit a signal, a METI signal, as was done at Arecibo with the famous Arecibo message? Can we do that with that telescope yet? Or is that something that is just not quite there for? It's a listening post still as opposed to a transmitting post?
Yeah. Your question is dead on. So Arecibo was a multi-purpose facility. It wasn't just for astronomers. It also had this big transmitter for radio studies of the atmosphere and for asteroids and planets. Arecibo was incredibly good at figuring out the orbits of distant asteroids and figuring out if they're going to smash into Earth. So it's very useful because these asteroids, they wiped out the dinosaurs 60 million years ago. A big asteroid smashed into Earth and changed the atmosphere and the climate. So it'd be good to keep track of these asteroids, and Arecibo was the best place to do that, figure out if they're going to hit us. It also, made these radar maps that could transmit out not just to asteroids, but bounce radio signals off the planets, and they got incredibly good studies of the planets and the atmospheres of the planets. So it was useful for a lot of different things, a lot of the atmospheric physics to understand space weather and how the sun disrupts communication. That's all done or was done at the Arecibo facility. And so they used it. They had a transmitter there. They didn't build it for communicating with ET, for sending messages to ET. They used it for studying the atmosphere and objects in our solar system. But that was the original goal when Arecibo was built, was to study the ionosphere, the upper layers of the atmosphere, and bounce signals off the ionosphere and figure out what it was made of and how it worked. So, and astronomy was kind of an afterthought. So, yeah, you're absolutely right. The FAST telescope doesn't have a transmitter. There are no radio telescopes that have transmitters, but there are other kinds of telescopes that are used for communication. NASA has transmitters to communicate with spacecraft, and there are other transmitters. But radio telescopes don't have transmitters, and FAST doesn't have a transmitter. But I actually think that's a good thing. I am not a fan of METI. I think METI is potentially dangerous. This idea of sending deliberate messages out into space, messages to space. So SETI, as you know, is a listening experiment. It's a passive experiment. We're trying to learn, are we alone? Is anybody out there? We're learning about the universe. So sending messages, perturbing the universe, kind of trying to provoke a response. And there are not very many people that think METI is a good idea. It's a very small fraction of scientists, way less than 1%. There's only a handful of people that advocate this. And most of us think, including myself, think that it's potentially dangerous. Probably the risks are low, but you're putting 8 billion people at risk on the planet. So even if you think the risks are small, you don't want to do something where, even with the risks are small, when you multiply the risks by 8 billion, that's a very dangerous thing. And also, it shouldn't be up to a small group of people. This is we're all at risk here. And so if you want to transmit, it should be up to, all of humanity on the planet. And it shouldn't be, made by a decision with a small number of people with access to a transmitter. I think, I think we should be listening at first. We should be just getting in the game, learning how to do this, learning more about the universe, learning are we alone or not. And then after we've been studying the universe and learn more about our place in the universe, and maybe learning about other civilizations, then we can talk about whether it's a good idea to respond, transmit a message and who should speak for Earth and what the message should contain. But I think we're too primitive a civilization for that. We don't know what's out there. They're probably going to, I would guess that they're not going to come and eat us. Maybe they've learned to live and they're not killing each other. We are kind of in this dangerous phase right now, very aggressive and killing each other and taking each other's resources away from each other. Hopefully they're not in that phase. An advanced civilization that's gotten through that kind of difficult bottleneck period maybe has learned to live together in peace, but maybe not. And so maybe they're going to come and, maybe Earth has polonium. Let's come and grind up their planet and get all the polonium out of the Earth's. I don't know what they're going to do, but that seems unlikely. But because there's so many people on Earth, I'd say don't do that until we know more about the universe.
Or the padded room scenario where they take notice that there's an intelligent civilization here and they come here to make sure to forcibly preserve us so that we don't destroy ourselves or can't. And then all of a sudden we're not in control of anything anymore. They're the bosses.
Right.
So listen very carefully before you speak. However, we have a problem. We may be already screaming our technosignatures out into about 100 light year radius, something like that. And that's only going to get worse. So we unintentionally are already broadcasting very strongly. The question is it strong enough for somebody within that distance to take a look at us and see our, high power radar or something like that and know we're here that way?
Yeah, that's an interesting argument. The people that are advocating to transmit, this small group of people, there are probably a dozen people on the planet that think this is a good idea that I know of. They say, well, there's low risk because Earthlings are already transmitting. And it's true. We got all this television. I Love Lucy's was transmitted 60 years ago, has gone past 10,000 stars. Ed Sullivan's gone past 10,000 stars. All those early television shows. FM radio goes out. That's been around for a long time. And the nearby stars have seen The Simpsons. But I think the counter argument is, well, if we're transmitting, why do you want to transmit? Then they say, well, we want to transmit much more powerful beam signals that are anti-cryptographic with language lessons and have a lot of information content. So I think what they do, they're kind of stuck in this weird kind of syllogism of logic that they're arguing, we're already transmitting and it's no big deal to add this one more transmission. Then you say, well, why transmit then? If we're already transmitting and say, our thing is fundamentally different. It's going to be more powerful and beamed and contain information. So I think that there is additional danger from this kind of deliberate broadcasting.
How big of a danger, though, do you think? Obviously we can't know, but when we look around...
Yeah, I think that's one of the problems is the risks are very difficult to assess. And so I think it's better to be on the safe side. So the people that deliberately transmit say the risks are negligible. What does that mean, negligible? So there are 7 billion people or maybe 8 billion people on the planet now. So let's say the risks are 1 in 1,000. That means every time you transmit, you're killing 8 billion divided by 1,000. So you're killing 8 million people every time you transmit. What if the risks are 1 in a million? Then you're killing 8,000 people every time you transmit. So even if the risks are minuscule, that's killing a lot of people on average. So, you multiply the probability by the population on the planet. So I don't know what the risks are. I expect they're low. 1 in 1,000 that they're going to come and do some damage or just grind up our planet in a millisecond. But I just don't know how to measure them. And these people that claim they know the risks, they don't know what they're talking about.
You can't know. But what you can say is that Earth has screamed its biosignature in the form of disequilibriums of gases in the atmosphere for a very, very long time, billions of years. So anybody in the galaxy with a big enough telescope could have looked at this exoplanet, Earth, and said, that hosts a biosphere. So in some sense, Earth always has already given us away. It's just whether the question is, if useful exoplanets with biosphere, if those exoplanets are useful, somebody would have been here by now and we would never be here. We would have never evolved. It would have been a controlled planet or something like that. So at least we can take some consolation, I suppose, in the idea that since Earth has been giving us away for a very long time, that must mean that this planet is not so useful for somebody to bother crossing space-time to come here and take control of, right? So if it must be predicated, their interest, on us being technological if they're going to take notice, right?
Yeah, I think your question is dead on here. So we've had oxygen on our planet for 500 million years. And so that means that anybody in the galaxy or even nearby galaxies could observe that oxygen. Of course, they have to have a much better telescope and technology than we do, but we would be observable for the last 500 million years. They would know there's simple life here if they have a good spectrometer, maybe not just oxygen, but a combination of molecules, so they could really clinch it. So they'd know there's simple life here. They'd have to be within 100 years or so to see smog in our atmosphere, or 100 light years, or to see radio pollution, television. They'd have to be within 70 light years. So that's a much smaller set of stars, because that goes out kind of spherically, goes out in all directions in that shell of our radio waves. Maybe if you watch Star Trek, you know about the Prime Directive. Maybe they know about us, but their ethics means don't go interfering with primitive civilizations like Earthlings. Maybe they realized when advanced civilizations get in contact with primitive civilization, not so good for the primitive civilizations. That's happened several times here on Earth. By advanced civilization, I mean just advanced technologically and scientifically, not culturally advanced, but that's wiped out. These less technological civilizations have been, their culture has been wiped out. And so maybe they think, maybe this is not a good idea. Let's wait until they're not killing each other and they learn a little bit more about how to take care of themselves and their planet, and then we'll reach out to them.
I think it would be absolutely delightful if the proponents of METI sent out a huge signal, and the only response we ever get from an alien civilization is, "Be quiet, we're doing radio astronomy."
Yeah.
and or even better, we're looking for more important alien civilizations. Keep your signals down, your interference. Now, in regards to the future of SETI, all right, now SETI's evolving, and we're getting into this sort of ideas of broader SETI, more all sky searches and things like that. Do you think that's going to give us a better chance of the detection of an alien civilization, as opposed to targeted, very, very carefully chosen SETI targets, looking at a star as opposed to looking at the entire sky?
Yeah, I'm keen on the content of your question, and I've been putting my life recently into what's called all sky, all the time SETI, working on a project called SETI, where we have 100 telescopes. We don't have this yet, but we're building it. We just have 2 telescopes. But the idea is to have 100 telescopes each one looking at a different patch of the sky, so we can cover an enormous part of the sky simultaneously. And the motivation there, as your question alluded, is that there may be kind of a signal that's not on all the time, maybe like a lighthouse, a flash. And maybe it's flashing once a week or once a month or once a year. We don't know. But if you just have an ordinary telescope, when you look at it, when you point it at a place in the sky, it's like it's looking at a little tiny patch of the sky. A big telescope looks at a millionth of the sky at a time. It's like looking through a soda straw 30 feet long, a little tiny little piece. So you're looking at one piece of the sky and the flash is going off somewhere completely different. And you're going to miss that. And we think there's a good reason why ET might have flash us. That would be a good way, just like lighthouses work. It doesn't take much energy to make a flash once in a while, maybe point at a different flash one star, then flash the next star. There are lots of reasons to do that. We call it pulse signals. It takes much less energy than transmitting continuously, and you can really get your attention. You wait a little bit, build up your energy, and then you can flash. We have lasers that are much brighter than our sun now. So it would be pretty easy to get to, and it's a good way to send high bandwidth communication. Anyway, there are lots of reasons why you might expect a signal to be pulsed or flashed. And so, but the problem is we don't know when the flash is going to go off and where to point the telescope. So SETI points all these telescopes in all different directions, and each telescope is specially designed to be very, what we call wide field. It covers a huge area on the sky. Each one covers 100 square degrees. There's 100 telescopes, so we cover 10,000 square degrees. Pretty big chunk of the sky simultaneously. We might be able to build it. If you write us a big check, we could have one on the other side of the planet in different places, so we could really cover the whole sky. SETI, I'm really excited about that because not just are we covering a big chunk of the sky, but we're covering a time scale that astronomers have never looked at before. Well, we're looking for flashes a billionth of a second long, or a millionth of a second long, or a thousandth of a second long. Astronomers, typically, they use these cameras where they open their shutter for 15 seconds or minutes or hours. And so these little short flashes wouldn't have been discovered yet. And what's really interesting in astronomy is if you want to make an astronomical discovery, a good way to do it is just look at something that nobody's looked at before, some new time scale or some new wavelength or frequency scale, or look deeper into the sky at a particular place or at a different band. And we don't understand why, but nature just seems to populate there's all these different size scales and time scales. There's phenomena everywhere you look. If you look at a new time scale, you'll find something. If you look at a new size scale, you find something. If you look at a new wavelength, there's something there. We don't understand why that's true, but it seems to be what nature does. And so we're looking at a whole new time scale. We're looking at a much larger place in the sky. So maybe we'll find something interesting. Maybe we'll not find ET, but maybe discover some new astrophysical phenomena. A lot of discoveries are made by just looking at some new, what we call parameter space, someplace nobody's looked before. You find something new. We understand why that happens in evolution, because if there's some ecological niche where there's food, there'll be selection of pressure for creatures will evolve there. So all the different kind of ecological places on our planet are filled with life. No matter where you go on the Earth, there's life. But we don't understand why that happens in nature and physics.
It's going to be really interesting, especially as instruments come online. I'm particularly excited myself with visual astronomy, with the prospect of all-sky surveys from the Vera Rubin telescope and what that can offer us. You're not taking a snapshot through a pair of binoculars. You're looking at the entire sky, which greatly increases your chance of seeing something. And that's what SETI is going to do for SETI and radio astronomy in general. My last question for you, though, is not really all that related to SETI, but it's interesting nonetheless. Your involvement in the early days of Silicon Valley with the Homebrew Computer Club, I believe it was called. What was that like? That included some very interesting figures.
Yeah, so everybody in that club got rich except me. So when I was in high school, the very first chips had come out, not to build sort of home computers, but they were designed by Intel, a little 4-bit programmable processor to replace cash registers. At the time, cash registers were mechanical things with gears and pulleys and dials and stuff like that. And they said, well, we could make a programmable chip to replace these mechanical cash registers with electronic cash registers. And they made it programmable. It wasn't just a thing that could only be a cash register. So these high school kids, and there were some college kids there too in this club, we said, let's get a hold of these chips and we made the first kind of home computers out of these chips. We made the first word processors and spreadsheets and home operating systems out of these chips of Earth. And then there were 8-bit computers and 16-bit, and it was all open source. Every time you designed something, the hardware was open, the software was open. We were all just exchanging ideas and software and hardware ideas. And in that club, Steve Wozniak and Steve Jobs were in that club, and they built a machine. A lot of other machines were as good or better than their machines, but they said, hey, we could sell these things. And they made a lot of money.
Indeed, they did. I'm speaking to you on an Apple product.
Yeah, I didn't get rich because I thought maybe we could use these chips to do SETI. So I wrote some code to analyze. It's called a Fourier transform code that could look at many channels all at once, looking at lots of different frequencies simultaneously to enhance the chances of success in SETI.
In the long run, it's better to discover an alien civilization than it is to make $1 billion.
I'm having a lot of fun.
All right. Thank you for joining us today. And I hope you come back at some point, especially if we actually find a signal, a good candidate signal.
I'll be sure to call you, John.
Absolutely.
Great questions, Sean. I really appreciate it.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.